Thanks, Ron, and thanks for coming. What I'd like to do is talk to you about cities, not just the building, but the city, and what it means to consider carbon and the environment in our designs. We've gotten pretty good about designing buildings efficiently and buildings that can be constructed readily, but we've got some environmental challenges, and the climate is changing, and there's a debate on why, but it's happening. So with this climate change, we need to consider our designs in a different way. How many of you think of LEED and think of the operation of our buildings in terms of emitted carbon? Probably most of us, right? But for most building projects, it takes 20 years for the carbon that's embodied in our structures to equate to the operational carbon that's emitted from lights, HVAC systems, and so forth. So if our buildings come out of service for any reason, the embodied carbon that is put into construction is actually more important than the emitted carbon over its life. Okay, so it's very important that we consider this initial stage. When we talk about embodied carbon, there are really three primary components. There's materials, there's construction, and then there's something that's very important, that's damage. And damage can come from various things. It can come from the environment, it can come from seismic issues, but this is something that we need to consider. And we need to consider buildings having a life. They're not there forever, especially in places like California. The building will have a considered life, and we should introduce that into our designs. So what we've done is we've been thinking a lot about this, and we've thought about the different components as it enters into an analysis that we need to set forth first to bring these issues to light, and second, come to some agreement on what our targets are for design. So what we've done is we've created a tool that is an algorithm. It's simply an algorithm that takes all of these components, and there are lots of them. We talked about that in the first presentation. There's the material itself. There's the time it takes and the carbon it takes to get that material to the site. There's forming systems if it's concrete. There's cement, and so forth. So what we've done is we've made it really simple. You can take these 5 elements and define carbon for buildings initially. And you can define it later in the design life. So number of stories, framed area, structural system type, expected service life, and the site conditions, wind and seismic. So this is an interface. It's a work in progress. We can debate it. But what this does is it takes those primary components and it comes up with a calculation for material, construction, and damage. And material is shown in blue, construction is shown in red, and damage, probabilistic damage, is shown in yellow. So if you take these two case studies that I'll show you, one's a shorter building and one's a taller building, and you apply these ideas, we'll see what we find. If you consider the structure as a conventional building, shear wall building with a flat plate as a baseline, and then consider it with an advanced system, a seismically isolated system. The building's located in San Francisco. And you look at the building in section, it's fairly similar. The basement's a little bit deeper with a seismic isolation system. But more importantly, what does it mean to carbon? So if you look at that chart on the right, there are a lot of numbers on the screen here. If you look at the chart on the right, this is the initial case with the building with a conventional design. Reinforced concrete core, flat slabs, and you can see that there's a target amount of carbon for this structure. And look at the yellow band. And as we designed the building, it looked at various options like viscous dampers. We were able to reduce the probabilistic damage over the life of this building, and the target life was 50 years. Okay, so it's 14 stories, 3 basements, the areas that are shown. And then seismic isolation. So we're able to reduce it further. So the impact because the amount of damage that we expect over the 50 years is less, the repair is less, the impact on the environment is less. So through the phases of design of this, we've got the core-only system to start. We've got a reduction in carbon by 5% if we introduce dampers into the system, and a 14% reduction if we were able to combine base isolation with the structural system, the core-only system. The second study I want to show you is a taller building. It's nominally 30 stories. It's in San Francisco. It's directly across from the Transbay site, which Ron and his team are involved with. And it's a fairly straightforward, hard-hitting developer-type building. Okay, so fairly regular floor plates. But the goal for this building was to come up with an idea that was far more environmentally responsible than a typical office building that you might see around the United States. And part of it was daylight. How can we introduce daylight into the spaces? How can we pack as many floors into this building as possible and make it more efficient from an economic point of view? So what we did is we looked carefully at the floor plan, and we came up with a system that's very straightforward. It's a core-only building. We optimized the floor, and the red areas that you see are areas of highest demand, and areas in blue are least demand. And we came up with a flat plate system that spans nominally 35 to 40 feet, depending on where you are, with a large cantilever in the corner that faces towards the Transbay project. And what we did is we said, okay, in the very beginning of the project, let's treat the building conventionally. Let's look at it as if it's a code-based design, which would include a core and a perimeter moment frame because of the building height. So we were able to reduce the amount of carbon in this building because we were able to eliminate the moment frame. So the advantage is economic, and it's also driven by the carbon that's involved with the building. So during design development, we were able to reduce the amount of carbon. We looked at it again during CDs, and in fact, the carbon that we had calculated with this program went up. We found that the material that we were putting into the project actually went up just a little bit. And then we revisited it again during CA, during construction, and we found that we were able to bring that carbon back down. And what's important about this idea, this algorithm, is that you can input the exact values. So the amount of rebar that you have in the building, the amount of concrete that you have in the building. So it goes from this conceptual idea of only knowing 5 components to something that gets very, very specific. So what we're able to do is reduce the material in the building, reduce the amount of carbon from a dual system to a core-only system through the phases of design. And again, moving toward this optimization, this idea of driving down the amount of material in the project. So there's the nominal span of 13 meters. What did I say? I said 35 feet. It's 43 feet from the core to the outside. It's an 11-inch thick slab. It's hyper-cambered, so we work with the contractor to create a cambered system that allowed for that slab system to come back to its level position over time. And there's a couple of images of the project under construction right now. So core, plate, and the idea of rapid construction, a drop system only at the lobby where we have a tall wall and the connections for that, and then the cantilever space that you get in the corner of the building. So David's going to talk about a couple of other specifics, most particularly about construction for this project, and then I'll come back up after he says a few things.
Thanks, Mark. So I want to talk about 2 items. The first will be getting into a little bit of the details of what we did during construction of this building, and then some forward thinking about some of the topics that we need to be talking about, particularly at a place like this with the people that are here. So one item in particular with this project that we did, being so close to our office, we visited it several times a week and took detailed accounting of the various people that were on site, what they were doing, the equipment they were using, the cranes that were being used, and had a very detailed accounting of what was occurring on site. And we used that to go back, look at those specific equipments, There's specific fuel and energy consumptions that would be used, and then calculated a final detailed carbon accounting of this office tower, which we believe is one of the few ones to be done, perhaps the only one on the West Coast looking specifically through the construction. We think there's been very few done. So we think this information is really valuable. We could have a whole presentation on that, but I just wanted to focus on one item, which particularly is the basements. Not necessarily the most interesting part of the building, but as we found, is perhaps the most carbon-intensive program that we put in buildings. If you think about it, we have a temporary perimeter shoring, we have excavation, and then we have below-grade construction, which, as many of you know, is one of the most time-consuming tasks that's in a project. So if we look at the embodied carbon in just the construction processes, those ones we went out and observed, we see a very carbon-intensive work relative to what's happening above grade. Our contractors are extremely efficient in above-grade work. This had a 5-day floor-to-floor cycle, mostly because of the volume of concrete. Some buildings get down to 3 days per floor. Very, very efficient. But I don't think we're as efficient as we need to be below grade. I don't think we're as efficient with materials or in our construction processes as what we need to be. It raises the issue of what's in the basement. It's usually some mechanical equipment and a lot of parking. I think we're at a little bit of difficulty with that parking. The client needs it for their financial picture. But it's difficult to have that where we want to see us going more towards mass transportation. But the bottom line is our below-grade work's very carbon-intensive. So this is a study that Mark actually did of some key buildings. Most of us are familiar with them, looking at the original World Trade Center, Sears Tower, Amco building, John Hancock, and finally the building we're in right now, the Jinmao building. Similar heights among those buildings. One of the key differences is the material type. And I think when we use materials efficiently, as it's been mentioned, and I think when we use materials in their most appropriate way, we find structures that can be not only cost efficient, but carbon efficient. And you can see on the right there's some normalized cost metrics, and there's also the carbon on a per square foot basis. And we see there's a synergy there, and that's something that we need to focus on. And this is not just the carbon of the material, it's of the construction processes and material from foundation to completion of the structural system. We have a database, unique in SOM, of hundreds of tall buildings that we can pull upon. We know their use, we know their geographic location, we know the material dispositions. We know quite a bit about them. This is a really interesting resource that we've tapped into. And we asked ourselves, what would it mean if we understood what the carbon of these buildings were? What could the data tell us about that? So we started investigating it. Each one of the dots you see on there is the embodied carbon on a per square foot basis of several hundred buildings that have been constructed, pulling from this database of information. Along the bottom is the structural embodied carbon. The size of the dot is the total amount of carbon. The color is relative to its use, so we can layer in this information and try to have the data tell us something so that we can project forward and learn more about how our practice should be from looking at our past. So we can start doing some breaking up of the data. We can start looking at what is the buildings that have very good embodied carbon levels when we look at wind or seismic or structural material type or use. We can start categorizing this data to learn more about it so we can understand to project forward. So these are two simple plots. The one on the left categorizes those buildings down by height, and the one on the right categorizes them by material. So on the left, we see that taller and taller buildings do have more embodied carbon. That's for two primary reasons. One is for more robust lateral systems. The other one is because of longer construction durations. On the right, we see it broken up by material. From this, we can start to see where we need to be focusing. I've been to several presentations in the past at conferences where I see people discussing, well, should we make it a 28-foot span or a 30-foot span? Which one's going to be more carbon efficient? And I think we as an industry need to look not at the small things, but at the big things. Where can we make a difference? So to try to quantify that distance, we've developed this tool that Mark talked about, the environmental analysis tool, which, yes, it does calculate embodied carbon, but it also looks at cost-benefit analysis of enhanced seismic force-resisting systems. It does a robust LCA. We can use it from concept through construction. And we've released it. It's a publicly available software now. You can go to som.com, search for the EA tool. You'll be able to download it. It's a free download. And we put it out there to have a conversation. And it's a very robust conversation. It's one we're having now. It's one we see coming up in many places. We see practitioners outside of SOM, researchers outside of SOM using this tool quite a bit. Thousands of buildings have been analyzed using this tool now, so we're very excited about that. And we hope that it adds to the conversations which is occurring and allows clients, structural engineers, architects to quantify these things, to have that conversation. So projecting to a little bit of a different direction here, I want to talk about a methodology we've developed that we like to call Parametric City Modeling. It's a different lens of looking at a building. It's looking at it from the digital perspective. So in San Francisco, we've developed with our architects what we call the San Francisco Digital Model, which is a very robust three-dimensional model, very accurate of the entire city. And it's a BIM model. We have building information included in this. When was the building constructed? Is it on liquefiable soil? Is it at risk for rising tides and rising water levels? There's many more factors that are in there, but it tells us about each site and how that can inform the site that we're in. So as part of this parametric city modeling, there's a specific algorithm that we're very excited about called the Building System Modeling Algorithm. It's a very robust algorithm which, given just a three-dimensional form, can slice that form up and estimate the net floor area with only knowing the location, the three-dimensional disposition of the building, the use of the building, the structural material type, and just a few other inputs. It can do that. And so what we've done is we've taken a few prototypical buildings. This is kind of a chart describing, well, what if we took a prototypical building and just increasing the height? How tall can we build from a net floor area perspective? And how tall can we build from a structural engineering perspective? Perhaps as a structural engineer, we could go up to 300 plus stories. But from a building efficiency perspective, perhaps there is a limit. And what is that limit? And that's what some of these studies investigated. So when we think tall, Burj Khalifa comes to mind, the current tallest building. Kingdom Tower is coming up right behind it. But there's something similar about those buildings. And looking at the disposition of floor plates, the structure, what we call the services, elevators, stairs, MEP, those things. We can break the building down in kind of these components. What is the DNA of a building? And we can look at, I'll say, the DNA of multiple buildings. So we did a survey of dozens of built structures looking at the different program requirements, I'll say, in a floor plate. And we use that information to understand what the leaf span is, what the different dispositions of these are. And we can start to quantify them in terms of their building area that's required. So we take those surveys that we've done on built buildings and we use this algorithm, this building system modeling algorithm. We compare it for accuracy. We find it's actually very accurate. Not only coming up with those different areas in the floor plan, but also looking at the leaf span. We found this to be very valuable information when we start looking at a city scale. So if we took those areas for all those buildings that we looked at, we can start to understand a little bit about the average program use of a floor plate. How much of it is structure, how much is stair, how much is elevator, what have you. So we took that algorithm to the Transbay district of San Francisco, a very rejuvenated area of the city that a lot of height limits have been increased by the city. And in particular to 350 Mission, the city wanted a taller building than what was there. And there wasn't structural reasons we couldn't get it any taller, or we could have gone much taller structurally. It was the number of elevators required to have a serviceable building. And then we asked ourselves, what are the height limits that should be in place in buildings as they're being planned? So this is kind of a plan view of the Transbay district, looking at two metrics, embodied carbon and net floor efficiency, of what I would say is prototypical buildings for each site. We took the height limit, the parcel, and understood, is this height limit that they are telling us we can build a reasonable one to do from a net floor area perspective and from a carbon perspective? The green ones, the answer is yes. The red ones, the answer is no. So when we're able to look at these two together, we can start to understand what is economical and what is sustainable for the sites concurrently in this kind of digital realm that we call the parametric city modeling. Now, if we took those buildings and we optimized their height, say, for concrete construction, having a 75% net floor area using concrete, we see that, yes, we can have a very, I'll say, dense urban area. And again, this is prototypical in terms of these are the optimal heights for the buildings, which, as you can see, vary differently from the actual heights which are currently allowed for the city codes. But we also see that it's very sustainable. So we need to be looking at building height limits from a planning level, even that early on, because that is where the biggest difference can be made. And we, as structural engineers, as architects, and I think the architects have been more involved, but we as structural engineers need to be a part of that conversation. We need to be informing cities what is reasonable and what is not. Now, if we were to take that and change it to steel construction, steel takes up less floor area. Perhaps we can build taller from a net floor area perspective, but it creates a very difficult situation in terms of embodied carbon. We would have much taller structures, needing more and more robust lateral systems. But if we bring that back with enhanced systems, viscous dampers, space isolation, what have you, we can start to get that under control. And when we start viewing cities from this holistic perspective, then we can start having a more sustainable future. So I'll turn it back over to Mark for the remainder.
We talked about carbon floor efficiency, and you would wonder, why is a structural engineer worried about floor efficiency in that area? Well, it's all about economics and the return on investment. So that's very important to our clients. It's very important to us. The more we can communicate this to our clients, the better. When we talk about seismic design, we're designing buildings to be damaged, in fact, and they're life safe, but from an economic and from a sustainability perspective, we can do a lot better. So our proposal is to increase resiliency, to increase environmental responsibility, and increase protection of investments by rethinking our goals. I think that we need to rethink and take our ideas beyond where we are currently and introduce ideas that are far more sophisticated. And a lot of this stuff is happening, okay? But we need to use techniques like this environmental consideration, to promote and support these more advanced ideas. It could be seismic isolation. It could be the joints within our buildings, and perhaps they behave in a seismic event much more like your body than a fixed joint that gets damaged. So the idea is protect the base building material, make the building environmentally responsible, and have that building back in service after the earthquake. So David's been involved, and I've been involved with looking at various aspects all at once. So we can take building form, we can look at efficiency, we can look at carbon, we can look at solar exposure, and we look at structure all at once when we're first considering buildings for sites. So the future and what perhaps we should think about. The idea of structures having multiple purposes is important. So every single component has at least two jobs. Perhaps it's safety, performance, but also perhaps it's things like controlling the environment within the building. It may be a system that looks at double walls, but it may be systems that look at dual purposes for structure itself. Looking at force flows, but also in the future material flows and the change of material characteristics over time, perhaps linked to ground motions and wind, so that we can change characteristics in response to these anticipated demands. So back to the carbon. We're proposing that we establish a target that all of us work toward. And this is a stab, it's a first try. But the numbers that you see, and they're included in the paper, are targets, a 15% reduction on what we think are achievable. So we can take these carbon limits and look at buildings over their heights and material types, but also think about challenging ourselves. What about international code requirements for this in terms of our design, beyond life safety? What about a rating system that considers it? And what about a carbon challenge that runs in parallel with the AIA for 2030 that looks at a reduction that's 30% rather than 15%? Looks at materials, it looks at systems, it looks at construction. So these are ideas, and we're trying to get the word out. And I think that we're glad you're here and listening to this, because it is, we think, a different way of thinking, and we think it's very, very important. especially as we move forward in these huge developments that are underway currently and we expect to happen over the next 50 or so years. So thanks a lot.